Yesterday, we talked about Gibbs free energy, and we talked about its equation. We said delta G is equal to delta H minus T delta S. We said we had two different equations. We had one that's going to deal with standard conditions. For standard conditions, 1 atm, 25 degrees Celsius. And we have one that's going to fall outside of standard conditions. So if we're working with something at 2 atms and 50 degrees Celsius, I need this equation here. So long as we're working at standard room temperature and standard room pressure, then we can work with this equation. And remember, the circles implies that this is at standard conditions. So here we go. Let's continue on here. So when it came to Gibbs free energy and that equation, one of the things that we said that we had three different possibilities here. And these three different possibilities are going to tell us whether or not the reaction to be spontaneous, whether it's reversible, or whether it's non-spontaneous. And we said if delta G happens to be negative, then it's going to be spontaneous in the forward direction, or we can say it's thermodynamically favorable in the forward direction. We said if delta G is equal to 0, then it's going to be simply at equilibrium. And then we said if delta G is going to end up being positive, then we're going to simply say it's non-spontaneous in the forward direction. However, in the reverse direction, it will be spontaneous in this case. For the sake of time, I'm going to skip over this slide here and go right here. If you look at the grid here, basically what this grid is showing us is the conditions that we need in order for something to be spontaneous or non-spontaneous in the forward direction. If it's going to be spontaneous, then that's going to be based upon having a delta H that is going to be negative. And once again, that's what the universe wants. It wants to go from high energy to low potential energy. Delta S, well, we want that to be positive because we want more chaos and disorder. Temperature is always going to be positive, so that's okay. And that's because we're dealing with the Kelvin scale here. If we have something going against Mother Nature, and in this case, when I mean going against Mother Nature, we're taking energy and we're making this thing go up higher in energy. Well, Mother Nature doesn't normally take things and make it go up higher in energy. If we take things and we make them more organized in this case, then that's also going against Mother Nature. And that's going to, both of these conditions are going to lead us to saying, hey, that condition of moving in the forward direction is going to be non-spontaneous. Now, if we have the following conditions, where delta H is negative and delta S is negative. And keep in mind that when delta H is negative, Mother Nature is like, yes, that's great. I'm going from high energy to low energy. But when delta S is negative here, then Mother Nature is like, no, that's awful, because you're now making me go and become more organized. So it's like you're giving her one thing here that's positive, she's happy about it, but over here it's like, no, this is not a good condition. If I want this thing to be spontaneous, if the delta H and the delta S is negative, we're going to see in a second that I just need the temperature to be low in this case. And if I lower the temperature enough, I can force this thing to actually become spontaneous. But at the same time, if I have a delta H that happens to be positive, which once again, that goes against Mother Nature, that simply says, hey, I'm taking something at low potential energy and I'm moving up to high potential energy. That's not what Mother Nature does spontaneously. But at the same time, I'm going to help Mother Nature out because I'm going to add more disorder. So she got something she wanted here that was positive, but here she's like, I don't like this because once again, that's just not what I'm going to actually do. If we have delta H and delta S both being positive, it's possible for this to occur at a high temperature. So let's take a look at these two scenarios right here and how lowering the temperature or increasing the temperature is going to cause this thing to become spontaneous, depending upon the conditions that we're dealing with. And once again, don't forget, delta G equals 0, that simply means we're at equilibrium. Here we go. So if we look at it, this is just a scenario where we have the delta H positive and also delta S positive, and I tell you that if we increase the temperature, I can make this thing become spontaneous. Now, the way that I'm going to kind of show this to you so you can kind of see it is I just made up some very basic, straightforward numbers. I just simply said for a specific reaction, maybe we're going to say that our delta H's are going to be positive too. So this is once again something that Mother Nature says, no, I don't like this. You're making me go up in energy. And once again, spontaneously, it goes lower in energy. Temperature, I'm just showing an increase in temperature going from 0 to 1 to 2 to 3 to 4 and so forth. So we're just increasing temperature. Right here, we're simply saying that, hey, when we look at the entropy then I'm giving it a positive entropy. And remember, a positive entropy simply means that we're growing with disorder. So I'm just going to define it as being 1. Once again, I'm just making these numbers easy as possible so we can kind of see what's going on here. So here we go. We got Gibbs' free equation that sits right here. And what you'll notice is that if I substitute these numbers into the expression, that initially, at low temperature, I'm going to end up having something that's non-spontaneous. And the reason why is we said delta H is going to be stuck at positive 2. So it's always going to be positive 2 right here. But if I look at my T delta S, the combination of the product of these two can cause this to become a more negative number, so long as I raise the actual temperature. Because remember, the delta S is a fix. So if I look at it, if I take 1 times 0, I get 0 here. If I take 1 times 1, then I'm going to end up 1 times 1, negative sitting right there, I get a negative 1. And when I add these two things together, because that's all we're doing is adding these two components together, I end up with a net value of +1, non-spontaneous. When I go to my delta S, or excuse me, raise my temperature in this case to now 2, and I multiply the 2 times the 1, because that's what I got to do right here, 2 times 1, plus the negative, I get a negative 2. Negative 2, positive 2, I get, in this case, 0, which means that, hey, the delta G is 0. It happens to be reversible. But you'll notice as the temperature continues to go up, this value right here, then what's going to start happening is my expression right here is going to start to outweigh that 2 that I have sitting right here. So you'll notice that, hey, -3 plus 2, I get a negative 1. It's now spontaneous. Raise the temperature even higher. -4 plus 2, I get a negative sitting right here. It's going to also, once again, illustrate that as the temperature increases, this part of the expression becomes more negative, and it beats out the positive part of the delta H. And that's always going to be the case, so long as I can raise my temperature up high enough to force this part of the expression to be greater than this part of the expression sitting right here. And if we look at it from the converse, where we have the delta H and the delta S both being negative, so I got them both being negative here, then what we're going to see when they're both negative, we're going to see something that looks like the following. This is going to be a negative value, which I simply said I'm going to define it as -2. So I just made it -2 right here. And remember, if I have a negative delta S, then a negative times a negative is going to make this part a positive. So this component will always be positive. But if you look at it, as I start to lower the temperature, so I'm going to decrease the temperature this time, I'm going to make this number actually smaller and smaller and smaller until, once again, the negative of the delta H here is going to outweigh the positive portion of this part of the expression, which is going to end up taking me from being positive to equilibrium to now where, hey, this number or this side of the expression becomes so small that the negative is going to outweigh it, and it now becomes spontaneous in this case. So the only thing I wanted to point out with this actual illustration is that if you have where the delta H and delta S are negative, just remember, negative, negative, lower temperature. If it's positive, positive, we want a higher temperature, and once again, we're really just trying to play around with this temperature to make sure that, once again, I always end up with a negative delta G. Here we go. So if we look at it, on this slide right here, that's in your notes, it simply right here provides you with the delta H and the delta S. And it simply says that in this reaction that we're looking at, is that it's going to be an exothermic reaction, which once again is a good thing. Also, it's showing that it's going towards more disorder. We got 2 moles of gas right here, going in this case to 3 moles of gas. So clearly, it is growing with disorder. So I can tell you right now that under this condition that delta G is going to be negative. And if you look at the choices that we got, it says always spontaneous, never spontaneous, spontaneous at low temperatures, or spontaneous at high temperatures. I know in this case it's always going to be spontaneous. Because it's always, when I substitute those numbers into this expression, it's always going to give me a negative no matter what. But at the same time, if we look at it, if I take this equation right here, which we said was going to be, in this case, exothermic. Exothermic means the delta would be on this side right here. If I flip this equation around, then it becomes endothermic. And what you'll notice is that's why we got the positive here. Also, now we're going from 3 moles of gas to 2 moles of gas. So once again, I can see that, hey, it's endothermic, it's becoming more organized. Universe is like, nah, this is not going to happen. It's never going to be spontaneous. But if you remember, I told you that if it's not spontaneous in this case in the forward direction, it simply means that it would be spontaneous going in the reverse direction, which we see right here being spontaneous. For the next one, if you look at this one, it simply says, hey, we've got, in this case, a exothermic reaction. Mother Nature's like, that's fantastic. But at the same time, you'll notice that the entropy is actually becoming more organized. And the reason why it's becoming more organized is I have 1 mole of gas on this side right here. I got a solid right here as well. But when this thing goes over here, I'm gonna have 0 moles of a gas. So clearly, once again, I got a solid and I got a gas. Over here, I just got this highly organized solid. So I can see that my entropy, once again, is becoming more organized. So if I have a negative and negative, and we're like, hey, you know what? What's gonna happen here? Well, I can tell you that basically what we're gonna need in this scenario is we need to make sure that we have a low temperature. And so long as we lower the temperature enough, then this reaction is going to end up being spontaneous. And that's because, once again, this would be negative as my delta H sitting right here. On this side of the expression sitting right here, I've got that negative there. Temperature is always positive. And then I've got this negative sitting right here that's associated with the delta S. This negative and that negative gives me a positive. I want that positive part of the expression right here to be as small as possible to make sure that the delta H is going to outweigh this part of the actual equation. And if we look at the next one, we got a positive and also a positive here. And that's, once again, just flipping these two equations around. So just flipping this thing around. And under that scenario, then my delta H is positive. That means that thing right there is fighting. It's like, I'm going to stop this thing from occurring. I don't want you to be spontaneous. But if we look at it, this part of the expression right here, I've got a negative that's sitting right here. Temperature is always going to be some positive value, so that's not going to affect anything. And then my delta S, in this case, we said was going to end up being positive. Positive times a negative ends up giving me a negative, which means that all of this expression right here gives me a negative value. I want that negative value to beat out that positive value. Make the temperature go really high. And therefore, this part of the expression is going to give me a larger negative that will beat out, in this case, the delta H. Once again, the rule of thumb, negative, negative, low temperature. Positive, positive, high temperature here. And once again, the answers that we just kind of went over are all expressed right here in the notes as well. So it gives you the answers on the next slide. One problem I just want to go over really quickly is this problem right here. Just in case something like this pulls up on the AP, hopefully you'll be able to solve this one. But for this particular problem, it says, hey, for ammonia, the enthalpy of fusion is, in this case, so the delta H of fusion is equal to 5,650 joules per mole. So I got that. It also says the entropy, delta S, in this case, entropy of fusion, is going to be 28.9 joules per Kelvin moles. So that's what I got here. And the question is, in this case, I believe I have a question there. There goes the question. Calculate the melting and freezing point of this ammonia in this case. Now, one of the things you got to remember is that when we think about the melting and freezing, looking at a heating curve here, I know that, once again, this is where the melting and freezing is going to occur. And because melting and freezing occurs at the same temperature, which is going to be 0 degrees Celsius, then I know what's going on here. That's an equilibrium that's existing. It's melting and also freezing, which means that one of the things I can do here is I can go to the equation that says delta G is equal to delta H minus T delta S. And what I can do is say, wait a second, if that's an equilibrium, because it's both melting and freezing at the melting freezing point, then my delta G for equilibriums, we said, is equal to 0. Which means in order to solve this problem, it's pretty easy. All I need to do is literally substitute in 0 for delta G, and then just plug in the actual values that were given to me. So I'm going to go here and just simply say, okay, delta G is 0, so 0 is equal to my delta H, so that's 5,650 joules per mole. And then I have minus the temperature, and then my delta S, which is going to sit right here, is going to be 28.9 joules Kelvin moles. And I just solve this thing for temperature. When I solve for temperature, what I do is take this, of course, bring it to the other side, so I'm going to have negative 5,650 joules per mole is equal to, it's going to be negative T times the 28.9 joules Kelvin moles. And then we just solve for T. Once again, bring this over here. So we end up now with negative 5,650 joules per mole divided by a negative 28.9 joules Kelvin moles. And that's going to be equal to the temperature at which is going to be the freezing and melting point of ammonia. And when I divide this number in, what do I get here? I get 5650 divided by 28.9. That gives me a temperature equal to 95 kelvins. So if they ever tell you something like, hey, what's the melting or the freezing point, and they give you the information for it, just realize that once again, delta G is going to be 0 because we're really dealing with these kind of equilibriums. That's where my vaporization condensation occurs, and this is kind of where my melting and freezing occurs. And that's why we said, hey, delta H of fusion right here. Delta H of solidification will be going this direction right here. But that's an equilibrium that would exist between the two. All right, so I just want to point that one out in case something like that did pop up. All right. Here we go. When it comes to the calculation of delta G, AP is going to ask you to calculate on this exam what the delta G is going to be. There's going to be two different ways in which you can calculate this. One way of calculating what the delta G is going to be, and once again, just want to figure out whether this thing is going to be positive or negative, and I guarantee you, if they ask you to calculate it, they're going to say, hey, is this thing spontaneous or non-spontaneous? You're going to go in and you're going to say, hey, you know what? I know that delta G is equal to delta H minus T delta S. It's at 25 degrees Celsius. I can put my little circles right here if I wanted to. If you left it off, it's not going to change anything. But what am I going to do here? As you'll notice that we did this earlier in the notes, where we figured out what the delta H was, because I gave you this heat of formation for each one of the reactants and products. So we just products minus the reactants, and we calculated this early on. Yesterday, we also calculated what the delta S was, because I gave you, once again, the actual different entropies for the reactants and products. So we said this would be the exact same equation that we'll use, and we can calculate what the delta S is going to be. Once I have my delta H and my delta S by using these equations, then I just substitute it in here. The only thing I have to be mindful of is two things. One, this temperature must be in Kelvin, so I'm going to have to add 273 to it. So that's going to be 298 kelvins. The next thing, this is really important because this is where I see so many students, when it comes to this sort of problem at the AP exam, lose points. It's an easy problem. But what a lot of students will do is they'll say, okay, I got this now. I'm going to take this number, I'm going to plug it in right here. Take the temperature, 298, put it right here. Take this delta S and plop it in right there. And I'm going to just put it in my calculator and figure out the answer. The problem you have is, look here. Delta H is in units of kilojoules. Over here, delta S is typically going to give it to you in joules per Kelvin. which means you got a choice here. Either you convert this joules into kilojoules, or you convert this kilojoules, and they just have to match up with their actual units. Once you match them up, then dump it into that expression and figure out what your delta G is going to be here. And you'll notice on the next slide, that's exactly what I did. I went ahead and said, you know what? I'm gonna go in here and take the one that was in joules per Kelvin and just convert it over to kilojoules per Kelvin. And then I went in here and I just substituted the values in, and this kelvins will cancel out the kelvins right there. I got kilojoules plus kilojoules, I get a negative value, and I'm gonna simply say, hey, this thing happens to be happens to be spontaneous in the forward direction, and that's because the delta G happens to be negative. If they ever ask you whether it's spontaneous or non-spontaneous and give your justification, literally your justification is just simply saying that because Gibbs free energy is negative, it is spontaneous. That's all you have to say. If it's positive, you're gonna say, it's non-spontaneous because it happens to be positive. So this is one way. This is a little bit lengthier, but once again, we can still do it. The easier way to get to the exact same answer is to use an equation that looks very familiar to us. The equation looks like this right here, where it simply says that, hey, I can do the exact same thing I did for my delta H's, my delta S's. They got an equation where we can literally just look up what the actual delta G is gonna be for each one of our reactants and each one of our products, and then we just go products minus reactants, and it will kick out, in this case, what the answer is gonna be. Now keep in mind, one of the restrictions that we have here is these delta G's are all at standard conditions. And remember, standard conditions, one thing I told you is 1 atm, it's 25 degrees Celsius. Also, one thing I forgot to tell you is that, what we're gonna see in a second, is standard conditions for concentrations is 1 molar. So we talk about standard conditions of a concentration, it's just 1 molar here. And the delta G for elements is gonna be 0. So it's a 0 delta G. It just, in this case, exists. It's not turning to one element or another spontaneous. It's like, I'm just here and I'm existing in this case. So here we go. Once again, delta G, we have positive, we can also have negative. But if we look at a problem here, such as maybe this problem, what I could do is, once again, provide you with the actual delta G's. And you can find these delta G's in the back of your textbook. So that's where I got the values from. From the back of the textbook, I just went in there and I kind of looked up what the delta G's for each one happened to be. And then I simply said, hey, I got 4 moles of this times this delta G. And once again, products minus, and then I went to the reactants. 1 mole of this times this delta G plus 6 moles of this times this delta G, and voila, I get to the exact same answer. And in your homework assignment tonight, I'm gonna have a couple of problems where you'll solve for the delta G this way here, just using the equation. I'll provide you with the delta G's. And then I'll have a problem where it might look like this one right here, where you had to go through and figure out what your delta H was, and also the delta S, and then bring them together in the actual delta G equals delta H minus T delta S. So that's kind of what you're looking at here. But calculating delta G is pretty easy and straightforward. All right, one more thing we need to talk about. As I told you that when it came to delta G, you can use this equation to calculate delta G at standard conditions, only at standard conditions. The problem we have is standard conditions are just so restricted. 1 atm, 1 molar concentration, 25 degrees Celsius. What if I want to work outside of those conditions? And if that's the case and I want to work outside those conditions, then what I have is I have this equation right here that simply says delta G at non-standard conditions is equal to delta G at standard conditions, which I can clearly just calculate by using, once again, this sort of calculation right here, plus RT ln of Q. And I'll explain exactly what you're seeing right here. This R that you're working with is going to be 8.314 joules, moles, Kelvin, and this R is actually found on the equation sheet. T, of course, is going to be temperature in kelvins, and Q is the exact same Q that we always know Q to be. It is going to be the reaction quotient. And remember, the reaction quotient is products over reactants is the way that we look at the reaction quotient. So, for instance, if I asked you to calculate, in this case, what we're looking at for the delta G at non-standard conditions, then one of the things I can do is, once again, just plug right into this actual expression. Now, let me point one thing out. Let's just say, hypothetically, I gave you the standard conditions of everything. If I gave you the standard conditions of everything, then one thing that you would do here is you would go in here and you'll say, okay, well, if I had the reaction of, just say hypothetically, A plus B going to produce C. So I got this reaction. What standard conditions says is it says that I gotta first start off with 1 molar of everything. Or if it's pressure, I need 1 atm of this, 1 atm of this, and 1 atm of this. I gotta start off with 1 of each. But if you look at it, under the Q situation, products of reactants, concentration of C divided by concentration of A times the concentration of B. If I put 1, 1, 1 here, Q is just gonna kick out and be 1. And if you put in 1 into this expression right here for the Q, the ln of 1 happens to be 0, which means that it says, hey, I already told you I'm at standard conditions. And once again, it just reaffirms that at standard conditions, hey, delta G is going to be the exact same thing as the delta G at standard conditions. But normally that's not going to be the case. They're going to ask you to try to calculate this at non-standard conditions. And if that's the case, then what we're going to see here is something that might look like the following. And here we go. So say I have this reaction right here. And I'm at non-standard conditions. And the reason why I know I'm at non-standard conditions is if it was at standard conditions, I'd have to have 1 atm of this, 1 atm of this, and 1 atm of this. So I'm not there. So what I can do is I can go and use, once again, my expression in this case. And when I look at the expression, what I would do here is I would go in and I would first figure out what is going to be my delta G at standard conditions. And this is where I would just simply use that products minus the reactants. I would go in here and simply say, okay, let me see what I got going on here. I've got 2 moles of this, so here you go, 2 moles of ammonia. I would take this number, which I will give to you, but once again, it could be found in the back of your appendix, but it's just the delta G that goes along with the ammonia. Here goes my product part of the expression here. Minus, and then I'm just doing the exact same thing for the reactants. And in this case, once again, we said the delta G of an element just exists, so it's 0 for this part right here. Plus, in this case, 3 moles of hydrogen gas, well, that's 0 also. And then what I end up getting in this case is I get a delta G, which is going to be equal to, in this case, negative 3,320 joules. So I've got this component right here. R, we said, is going to be the 8.314. Temperature in this case is going to be my 298 kelvins. Only thing I need now is just to figure out what my Q is going to be here. And if you remember, when it came to Q, it's products over reactants. Everybody raised their coefficients, no solids, no liquids. So that's exactly what I did here. Here's the partial pressure in this case of ammonia squared, partial pressure of the nitrogen, once again, which was given to me, partial pressure of the hydrogen cubed, and I figure out what my Q is going to be, and here we go. I substituted now my Q into this expression, and I go through and I solve for delta G at non-standard conditions. I get a negative value that's sitting down here, and once again, it just affirms that, hey, this thing is going to be spontaneous at non-standard conditions. Now, let me point one thing out. Normally on the AP exam, they're not going to ask you to do this calculation. It's just a lot going on here. I got to figure out my delta G. That's not too difficult to do. If I look at it, figuring out the Q, I mean, it's not overly complicated, but it takes a little bit of time here to figure out what the actual Q is going to be. Substituting all this stuff in and figuring out what the delta G, it just takes a little bit of time. So a lot of times they're not inclined to ask you this, but instead, what they're more inclined to ask you is going to be something along the following. And once again, we said this is definitely going to be spontaneous in the forward direction. And before I show you what they're going to be more inclined to show you or ask you, I just want to show you one other thing here. Technically, I could have told you this was also proceeding in the forward direction as well, if I was given a little bit of information here. So delta G says, hey, it's spontaneous in the forward direction. If I would have given you this information right here, where I showed you the actual equilibrium that exists between nitrogen, hydrogen, and ammonia, and if I provided you with the actual Kp, then when you went and you calculated your Q, if you were just given this, you could also affirm that, oh, this has to proceed in the forward direction because Q is 0.0093. And remember we said when we compare Q to Kp in this case, I need this Q to be that number right there. And the only way it can grow to be that number is I need this thing, or the numerator, to grow, which means this equilibrium is going to shift in the forward direction, which means it's spontaneous in the forward direction. The same thing that the actual equation is saying right here. But this is what we saw earlier in the second semester. This is just showing there's another way in which we can actually get there as well. All right. And once again, I'm going to explain how we're going to kind of shortcut this equation and how we're not going to really use it on the AP and what the AP is going to ask you to do with it. All right, really quickly, if we look at this expression that we have here, once again, calculating delta G at non-standard conditions. If by chance delta G happens to be at equilibrium at non-standard conditions, so hey, at non-standard conditions, I'm dealing with the equilibrium, then we said under that condition, the delta G will become 0 in this case. And that's why I substituted 0 right here. Also, if I'm at equilibrium, I'm no longer dealing with the Q here. I know that I can replace the Q with the equilibrium constant because we're at equilibrium here. And when I solve this expression, one of the neat things about this, all right, and you can take off.
Yeah.
All right, I'm going to continue on with this lecture. And the reason why I'm continuing on a little bit is when I first started the video, my iPhone stopped because I ran out of capacity. I didn't have enough storage. So I had to start the video all over again and go through about 10 more minutes of the video. I had to go back over 10 more minutes of the video. So I'm going to spend about another 10 minutes just going over this portion right here. And then we're going to call it a day in this case. So once again, with delta G, at equilibrium, it is going to be, once again, 0. So I got that here. Solve the expression. I now have this new expression. I'm just simply going in here and solving under the standard conditions. And if I solve for delta G at standard conditions, then I get this sort of expression right here. Now you might ask yourself, well, what are we doing with this expression? Why is it even relevant? You already told me, Mr. Harrelson, that this thing happens to be at equilibrium. I'm done. I know it's at equilibrium at non-standard conditions. That is true. We know it's at equilibrium. But what is cool about this expression is that if I know that it's at equilibrium at non-standard conditions, then one of the things I can do is I can always go figure out what the delta G at standard conditions is going to be by using an equation of products minus the reactants. I know the temperature at which it's at equilibrium, so I can plug that in here as well. What I can do with this equation that's really nice is I can actually now find what the equilibrium constant is going to be. You don't have to tell me the equilibrium constant anymore. Only thing you got to do is tell me, one, it's at equilibrium. Two, I will go and find your delta G, because once again, I can just look in the back of the appendix, get the delta G for my reactants and products. I can solve for this thing here. Temperature of the equilibrium, I already know. I can solve right there for K. And once again, I don't need anybody from this point on to tell me what the equilibrium constant is going to be. I will tell you, so long as you just give me the delta G's of the reactants and the products, and you just tell me what temperature the equilibrium is going to take place at. Now, one of the things you're going to notice here is I went in and I manipulated this expression to solve for what the equilibrium constant is going to be. And when you look at it, all I did is I raised, in this case, I'll show you just really quickly. I took and I divided this side by negative RT. So I get negative RT over here. So this is going to kind of like cancel out. And then I just raised both sides to its base of E. This is how I got that E is now negative delta GRT, and E to the ln is just going to cancel out and leave me my K right here. Which means that if I want to calculate, in this case, what my equilibrium constant is going to be, All I have to do now is just substitute in my delta G here, put the 8.314 right here for the ideal gas law constant that's on your actual equation sheet, plug in the temperature, and once again, I can tell you what the actual equilibrium constant is going to look like. So for instance, here goes ammonia. We worked with ammonia a lot in this class when we looked at equilibriums. And I would always have to tell you, well, the equilibrium constant for this is going to be, and I provide it to you. But if you look at it now, I don't have to provide it. Because what you could do is you could go in and say, okay, well, let me just go ahead and substitute it as an expression. So let me go to the back of the textbook, look at Appendix C. I'll find out, hey, the delta G for ammonia is right here, times the 2 moles, products, minus the reactants that we said, because these are elements, they're 0. Here goes my delta G sitting right here. I'm going to substitute in my delta G, being mindful that, once again, that R value that's given to me, once again, it's on the equation sheet, it's in units of joules here. I need to make sure that I convert this kilojoules to the joules, so the joules can cancel out, and then I can get, in this case, once again, my equilibrium constant at the given temperature that was provided here. And for this experiment, or this calculation, we said 298 kelvins. But if you look at it, if somebody said, hey, you know what is the equilibrium constant at some other value of a temperature? No problem. I can always just substitute in the new temperature right here, and it will calculate exactly what the equilibrium constant is going to be. So that's the really cool thing about this actual expression. It's just the fact that I have a way to actually get to that equilibrium constant. Now, I just want to do this last slide, this slide here, and one more slide, and we're done here. This slide I want you to see because I need you to understand that when we're looking at this expression here, wait for that bell to ring, we got about 5 more minutes and we'll be done here. If we look at it, one of the things that I can tell you is that if I have this expression sitting right here, and if somebody is saying, hey, you know what? We're going to plug in a R here, which once again is just a constant. They're going to be a temperature, which is always going to be positive as well. The only thing that's going to dictate this delta G as being possibly negative or positive is going to be the K that's sitting right here. And I want you to kind of see this, and I'll show you an actual multiple choice AP problem on the next slide. And they might ask something, and it's fair game in this case. The only thing you need to realize, and it's kind of like a review of the natural law, is that if the actual natural law is greater than, wait a second, make sure I got this right here. Yeah, if the natural log, or in this case, the K, happens to be greater than 1, so it's greater than 1, then what you have to realize is that the natural log is going to end up being positive. And if this is now positive, that means that positive is going to hit the negative, and look what we get here. We get delta G is going to be negative. It is going to be spontaneous. But at the same time, if I have a negative or a value less than 1, not negative, but less than 1 in this case, then what's going to happen is that's going to mean that the ln of that value of less than 1 is going to always produce something that's negative in this case. And because it's going to be a negative coming out here, the negative is going to hit the negative, and it's going to give me a positive, and we're going to be like, hey, it's non-spontaneous. Now, of course, if the natural log happens to be 1, then it's simply going to say, okay, well, hey, under that condition, then you're going to end up being, in this case, at equilibrium. So it's simply saying, hey, I'm going back and forth from that equilibrium under this condition here. So these are the scenarios that you're presented with. And if you ever forget, kind of think about it like a log. Natural log versus log. If I have a log of anything greater than 1, like, hey, 1 times 10 to the second, then that's going to give me the number equal to 2. If I had a log with a number less than 1, like 1 times 10 to the negative 2, then that's going to kick out negative 2. So it's the same kind of thought process here. If it's a positive or greater than 1, positive, it's negative, I get a negative here. If it happens to be less than 1, then once again, that's going to give me a negative here, hit the negative, and it's going to become positive. So if we look at this last problem here, and then we are going to pretty much call it a day. This particular problem simply says, hey, a reaction above, so we got this reaction, is not thermodynamically favorable at room temperature. However, it is favorable at lower temperatures. Based on the above information, which of the following value KEQ and sign of delta G for the reaction at low enough temperature to become favorably thermodynamic in this case? So, if you look at, so based upon the above information, which of the following KEQs and signs of the delta G for the reaction at a low enough temperature to become, in this case, favorable? Okay. So, I'm going to give you a couple of seconds. I'll give you like 30 seconds, maybe a minute, to just look at it and see if you can figure it out really quickly. All right, so if we look at it, all you have to do to solve this one is you're gonna go delta G is equal to negative RT ln of K, because we got an equilibrium here. So they're saying, hey, you know what? We want this thing to be spontaneous. So we want the sign of this thing to be spontaneous in the forward direction. And how is this going to be possible? Well, first of all, if I look at it, if I want it to be spontaneous, that means I know that my possible combination of answers is either going to be this answer here or this answer right here. Because I need my delta G to say, hey, I don't want this thing existing in equilibrium. I want it to favor going in the forward direction right here. And the next question is, okay, if I wanted to go in the forward direction, how do I want, in this case, this K to sit? And if you remember, we said, hey, if the K happens to be greater than 1, then this value of all of this is going to end up being positive. When it means it's going to hit the negative, I'm going to get a negative delta G. So if I look at it, it looks as though the one that I want to choose would actually be the bottom one right here, because that's going to give me a K. Once again, when I plug in, that's going to be positive, I'll hit that negative there, and I'll get a negative number out. And yes, it's going to be negative, and therefore it's spontaneous in the reverse direction. I wouldn't choose this one, because that's to the negative 38. And if that's a negative sitting here, because it's smaller than 1, that means that this ln of K will be negative, and hit the negative there, give me a positive, and this thing is not going to work in this case. All right, I know I told you this last slide, but this is the last slide right here. Once again, what we're looking at here is we're looking at, is this process spontaneous? And remember, if it's spontaneous, my delta G is going to be equal to negative. And we can say it's thermodynamically favorable. If the delta G happens to be equal to a positive, then we're going to simply say, oh, no, it's not spontaneous in the forward direction. However, in the reverse direction, it will be spontaneous. And then the last part is the equilibrium, and that's where delta G is going to be equal to 0. And if it's equal to 0, then we simply say, hey, it's under equilibrium conditions. So we're just using Gibbs free energy to make the determination whether it's spontaneous, non-spontaneous, or equilibrium. All right, for homework, all you're going to do is you're